How's everyone doing today? At least one thumbs up. Glad to see. So, first of all, double checking. Has anyone not picked up their test yet? All right. Moving on from that, midterm scores went out this morning. They should have. I submitted them in time. If you have any questions about what your actual percentage score is, since the midterm is just a vague letter grade, please let me know. I will gladly tell you. Your grades are not a secret in here. I will share that information with you anytime. And I'm also working on getting it displayed on Brightspace for you. So at any point, I'm glad to calculate your average, also run some calculations if you want to know what you need to make on the final to get a certain letter grade in the course. I'm happy to figure that out with you. So let me know any questions you have about that. Main thing for today is we're going to start chapter 6, which will be about momentum and collisions. We're kind of entering the latter half of the course here. So before we start that, any questions, needs, concerns, etc. from you guys? All right, and let's get started. So, chapter 6 will be about momentum and collisions. Those will be two kind of parallel themes all the way through. It's not going to be one followed by the other. They're both simultaneously the primary focus. In a second, we're going to define collisions and then define momentum. But before that, I actually want to ask real quick, kind of just a cursory question. Momentum is one of those physics words that is, at least sometimes, used in English vernacular. So my first question to you guys is, when you hear the word momentum, what does it mean and how is it commonly used? What places do you hear the word just used in everyday English?
Momentum, you think a moving force?
Motion. Very good. Momentum is directly and very specifically tied to motion. What sort of context do you hear about momentum? Namely, large amounts of momentum.
Like a plane, flying.
Okay. Yeah, planes have to move very fast. Correct. That's actually a pretty good example. Planes have a lot of mass and have to be moving very fast in order to stay in the air, since the way that the wings work, they generate lift based on speed through the air. I think that the place I most often hear it, just again, not really every day, and I don't even watch enough sports for it to be every day for me, but sports announcers will say a team has really built up momentum this season. They're really hard to stop. They got a groove going. I want to use that as the starting baseline. Something with momentum is hard to stop. Does that sound consistent?
Yeah.
All right, so with that in mind, let's begin defining our terms for the chapter. First, collisions. You guys know what a collision is, at least on the basic level, but the physics definition we're going to use for it is an interaction between two or more objects that come into direct physical contact with one another. Over a period of time, those two objects will exert a force upon each other. Specifically, they both exert forces, if we're assuming a two-object collision. They are both exerting force on each other. This is due to Newton's third law. If A acts on B, B acts back on A. You would know this if you've ever run face first into a door. You exert a force on the door hopefully opens. The door exerts a force on you, therefore your nose hurts. I speak from experience. The forces involved in this collision are going to cause the two objects involved to accelerate. This will cause their velocities to change over that aforementioned time interval, and this change in velocities facilitates transfer of both kinetic energy and momentum between the two objects involved in the collision. And that's gonna be kind of the part we're focusing on this week, this coming week. So, all collisions take a certain amount of time. It's likely an amount of time too fast for the human sensory system to track without aid. For example, I'm gonna be doing this a lot today. I'm gonna drop this golf ball on my desk, so noise warning ahead. How long is the actual time of the collision between the ball and the desk take?
Split second.
Split second. You probably blinked and literally didn't see it happen. I blinked. I'm sensitive to noise. Very small amount of time, but it's not technically instantaneous. It does take a certain number of milliseconds. And that's why you can watch it happening on, slow motion or a high-speed camera. Kind of to go back to chapter 5 real quick, because this thing bounced, it's kind of weird to think about because golf balls are typically thought of as solid, but because this thing bounced, it actually did compress for a second and contain elastic potential energy. It's just because the whole collision happened over like a nanosecond, it was too fast to see. But if you slowed it down enough and had enough measurement equipment to notice it, you could actually notice the golf ball squish slightly on impact. And then the process of it striking the table, squishing, going back to normal, and rebounding would all take a certain non-zero number of seconds. Milliseconds, but it's not zero. It does take time. And that time, most of the time for collisions, is going to be a teeny tiny number. And over that time, the velocity of the object changes, possibly by a lot. If you're doing a crash test and a car goes from 60 to 0 upon hitting a wall, that's a pretty big change in velocity, but it's an even bigger change if the object turns around as, impact ahead, as this thing does when it hits the floor. Turning around is a really big change because you go from one direction to the other. So, very big changes in velocity have a tendency to happen over very small intervals of time, and that creates big or small accelerations. Big. Big delta V over teeny tiny delta T gives it a really big acceleration. Big acceleration of an object is caused usually by pretty big forces. So those big instantaneous crashes have a lot of force involved in them. And that force, again, causes acceleration, change in velocity over time. The change in velocity is the part we're going to focus mostly on this week. Because again, this illustrates if speed is changing, that tells us kinetic energy level must be changing, since kinetic energy level depends on velocity. And it's also going to tell us that momentum level is changing, because momentum is also going to depend on velocity. And again, it happens over time. We're not going to ignore the time of impact. It's going to come up at some point. Questions so far? All right. Now, before I move on to define momentum, I kind of want to briefly compare it to kinetic energy and kind of why we're talking about momentum specifically in this section. I'm going to drop the golf ball again, so noise ahead, but I want you to especially pay attention to the height I drop it from versus the height it rises to. I'm going to try to catch it at its apex. Notice the difference from start to finish. Why does that happen? We've kind of been assuming that objects tend to go back up to the height they start from. At least that's what we assumed for a couple examples in chapter 5, but why didn't that happen here?
Well, there's gravity pulling it down after it goes back up. The force that the table exerts back onto it is not the same force to get it up to the height you dropped it from.
That is true. It has to do with the collision that exerts the force. You're right. And within that collision, the force of the collision does work on the golf ball. That's going to transform the type of energy the ball has, because that energy goes from GPE to KE to EPE back to KE, back to GPE, but it doesn't have the same amount of GPE as it started with. There's less energy here, and it's because it loses some, like some of the energy just leaves the ball entirely on impact. Kinetic energy is notoriously hard to track during a collision, and that's because energy has lots of different forms it can take. We can see the height difference, but we can't see where all the energy went, because there's lots of different forms it takes, right? Some of it's going to become heat because of friction to the air. Some of it's going to just become heat in the desk because of the impact. But another weird place that energy tends to go in collisions is sound. Sound is moving air, correct? You've heard this before, I hope. In order for the human ear to hear, vibrations have to travel through the air from source into your ear. And if the air is made of matter, not a lot of matter, but it's made of matter, so for air to move, it needs energy. Sound is a ripple of kinetic energy traveling through the air. And that means if energy is traveling from here to your ear, that's less energy in the golf ball. If you heard something, it means that whatever made that noise transferred some of its own energy into the air to create the sound wave. So by virtue of being able to hear the ball hit the table, that's proof the ball has less energy than it started with. To kind of compare this golf ball to, say, a rubber bouncy ball that you might get out of a vending machine at the grocery store when you were 5, dropping the coin, spin the thing, the ball falls out, and then you lose it in 5 minutes. Do those things make nearly as loud a noise? No, because the bouncier something is, the more elastic the collision it tends to have, the quieter it tends to be, right? That's because it's surrendering less of its own energy to sound. So the bouncy balls tend to be better, but even they will still lose energy over time because energy is really pesky and turns into lots of different forms, especially heat. This is one reason why we're focusing at least partially on momentum for now. Energy, kinetic energy, turns into all kinds of different forms, but momentum only has one form, so it's easier to track. There's lots of forms of energy, there's only one form of momentum. Questions thus far? All right, now we can define momentum. Momentum can be thought of as a measurement, a numerical measurement of how difficult an object is to stop. The more momentum something has, the bigger that number, the more difficult the object will be to bring to a complete stop. That's why I tried to describe it earlier the way that I did. The formula for momentum, I'm going to read the whole thing out loud. Rho equals mass times velocity. Frustratingly, the m is not the momentum, the m is mass. It's always been mass. The rho is momentum. That is the Greek letter rho, spelled as such. We're entering the part of the course where more and more Greek letters are going to start popping up because, English-speaking physicists ran out of letters a long time ago. They had to pilfer a lot from the Greek alphabet. I assume at some point in the future we'll have to start stealing from the Cyrillic alphabet too. Or any other alphabet of your choice, really. It's the Greek letter rho. I don't have a good explanation for why they picked rho instead of something that looked more like an M. Maybe in Greek, the word for momentum began with a rho. Could be a translation thing. Could be that, honestly, you can just call it rho-mentum if you want to. I won't stop you if that's a good way to remember it. But it's technically the letter rho. I'm telling you this because I'm going to say rho when I read the formula out loud. That's just ingrained in my brain. So when I say rho, I mean momentum. I'm referring to that letter. It's basically a P, but it's smoother than a P. at least the way that computers tend to use it. This marker's dying. Rho, P, uppercase P. If a computer's doing it, rho is smooth at the top left, whereas a P tends to have this little stem, kind of like an apple. It's not a big difference, and that's why a lot of textbooks, and frankly even your formula sheet, just use the letter P, but I call it rho. I want to make sure you know that, since that's what I'm going to be saying. So rho equals mass times velocity. The two things that determine something's momentum level are its total mass and its current velocity. This means the faster something is moving, the more momentum it has, and therefore the harder it is to stop. Does that sound consistent with your metric of reality? Yeah, especially if you've ever driven a car on the interstate and had to slam on the brakes because you crest over a hill and suddenly see 3 miles of traffic. If you're moving very fast, it's pretty hard to come to a complete stop all of a sudden. But the other part of it is mass. The more mass something has, the harder it is to stop. You know this if you've ever driven a truck at interstate speeds and had to hit the brakes. So those two things combined form momentum. The rho is the momentum itself. It is a vector. That's why the rho is underlined along with the velocity. Basically, the momentum just kind of inherits the direction of the velocity. Since the v is not being squared or anything like that, it just keeps the direction all the way through. Basically, it means if your truck is moving east, it wants to keep moving east, and even if it has to plow through a wall to do so, it'll still be moving east after the fact. So it's a vector, and the last thing, the unit for momentum is kilograms times meters per second. It does not have its own unit. I presume the reason for this is no unique scientist ever put their name on the unit, largely because most of Western physics work and thoughts on momentum actually came from Newton. And we already put his name on the force unit. I don't know why they didn't just call it an Isaac, because the man has 2 names, but they're stuck with kilogram meters per second. It's a pain to say out loud, but thankfully if you don't remember it off the top of your head, it's pretty easy to just determine on the fly, because kilograms times meters per second. It's weird, but it's thankfully not that complicated.
So after writing momentum, we put rho kg in this.
Oh yeah? Oh.
Unit, like the unit after we find the momentum.
Yeah, like for example, if you're giving me an answer, rho equals 5 kg ms.
Okay, alright, so there's no specific letter for that or anything.
Nope.
Right.
Yeah, it's the weird part.
It's like joules is kind of kilograms times seconds.
Yeah, I think it's the first, no, okay, it's not the first composite unit that we've had, but it's one of the more prominent ones. We've had Newton's per meter, and in a couple of weeks we'll have Newton meters, which is different for some reason.
3D.
Rotational, actually. We'll get to that 2 weeks from now. It's its own unique headache. Questions on any of this information so far? All right. New formula, so let us begin a little bit of practice with it. Here we have 4 different scenarios, 3 of which feature objects, 1 of which features an organism, all moving at different speeds. Please tell me, either by guessing or by quickly calculating, which of these scenarios features the most momentum. Place your bets now. Cue the Jeopardy music.
Car.
We have 1 vote for car.
Window. Dog.
1 vote for dog. Any agreements or disagreements? vote, and dog wins. Why is the building immediately disqualified? It's not moving. It doesn't matter how massive something is, if its current velocity is 0, it has no momentum. It's very easy to stop because it has already stopped. If the building was moving, it would have a lot of momentum, and then we'd have many different problems. The bullet has a very large amount of velocity. However, its mass is teeny tiny. And before you go multiplying 10 times 1,000, note 10 grams. So we have to turn that into kilograms first. So 0.01 times 1,000 is only 10 kilogram meters per second. I'm already sick of saying that unit, frankly. I'm skipping C for a second to look at D, which is kind of the polar opposite of B. Here we have a very massive object moving incredibly slowly, 2,000 kilograms at 1 centimeter per second. This needs to be turned into meters per second first. Coincidentally, this also converts to 0.01. So that's 2,000 times 0.01 is only 20 kilograms. And that again leaves the dog as the winner because its units are already in the correct forms and don't need to be converted. So 25 times 10 is 250. Weirdly, the dog, out of all 4 of these scenarios, is the hardest to stop. The car is moving slow enough that you could probably stop it by just putting your foot on the bumper. 1 centimeter per second is like slower than idling speed. It's like idling uphill. Meanwhile, I've seen a few videos of dogs being like trained for defense purposes, and therefore I've seen videos of a canine running full tilt at a guy in one of those big, protection suits that make it impossible to move in. If the dog barrels straight at a human torso and just cannonballs, they are falling over. Dogs are dense, and they can run fast. I know this because I keep wanting to call her a puppy, even though she's 2 years old. Problem is she's just short and stupid. This puppy, low to the ground, about 40 pounds, runs really fast, and frankly, because she's so low to the ground, if she tackles my shins, I'm not standing up anymore. Questions? All right. Now, before the next formula, brief disclaimer. I've mentioned the notion of inertia before, mostly in regards to Newton's first law of motion, the law of inertia. An object at rest remains at rest, and an object in motion remains at constant motion until acted upon by an outside force. Momentum is a similar concept, because if something has momentum, it wants to keep moving in the same direction at the same speed, right? And inertia kind of tells you the same thing. An object at rest stays at rest, and an object at motion remains at motion. Same speed, same direction. So the definitions of inertia and momentum do overlap, but they are not identical. Because momentum only exists when you're moving, whereas inertia still exists if you're not moving. If you're not moving, momentum is 0. But if you're not moving, you still have inertia. Because inertia just depends on mass. Because that first law, the law of inertia, says an object at rest stays at rest. And its inertia, its mass, tells you how much it wants to stay at rest. More mass, the harder it is to get it moving. So inertia is similar but not identical to momentum. They kind of overlap in terms of their domains. Inertia is a scalar that can exist at rest. Momentum is a vector that requires motion to exist. And then they further overlap both of them with kinetic energy, which also requires matter and motion. But they are all different things, as we will continue to discuss. Does that feel okay for now? All right. Now, let's look at how we're going to apply momentum in the coming week. In chapter 5, we talked about the law of conservation of energy. the idea that in any kind of process, however much energy exists in a system will remain consistent from start to finish, even if that energy is in a different object or is in a different form, or both. The total amount of energy from start to finish across all types remains constant. And the same is uniquely true for momentum. We're going to be using this to look at, again, collisions, was on the title slide. And collisions distinctly have a before state and an after state, kind of like the energy processes we were looking at. We would look at, say, how the energy transform in something as it rises and falls, KE to GPE to KE, and other processes like that, a distinct before versus after. And momentum in a collision is the same way. All collisions have a before and an after. I'm going to bring up crash tests a lot this week because, man, I watched a lot of Mythbusters as a kid. The before state of a crash test is car is barreling at a wall at speed, and the after state is car is stopped, the front bumper is pancaked, and the brick wall is probably broken. The car is also probably broken. Distinct before versus after. But across those states, not only is the total amount of energy in all forms conserved, so too is the total amount of momentum. The momentum is actually easier to track because there's only one form it can occupy, and that is momentum. When we're doing those energy calculations, we had to think about all the different forms of energy that could exist at each stage, but instead, momentum has no other form. We don't have to track different types of it, it's just the one thing across multiple objects. But I want to make sure you know, total momentum is conserved like the total energy was. And that's what we're going to be working on improving in the coming week. Excuse me. So these questions will actually work kind of similarly to the conservation of energy questions we did in chapter 5, some of which made it on your test. This one, I mean, the starting formula already looks pretty similar to the conservation of energy formula, but I'm not going to demonstrate how this works in the context of a collision. Questions before we do that? All right. So let us actually cause a collision. We're just going to shoot an arrow at a log. We're going to put a log on a fence post and fire an arrow at it. So let us define our before state versus our after state, our initial versus final. Initially, before the two objects collide, we have an arrow hurtling through the air at 25 meters per second. The mass of said arrow is 10 grams. And the log it is careening towards has a mass of 5 kilograms and is not initially moving. So here is our initial side. Examining this initial side, where is all the momentum to begin with? In the arrow. I saw a few people mouth it. Yes, the arrow is bringing all of the momentum to this party. The log doesn't have any to start with. And as we're going to kind of demonstrate, the total amount of momentum the arrow is bringing is going to end up being shared across both the arrow and the log after they collide and stick together. Basically, the arrow is bringing all the food to the party and the log is going to eat most of it. So in our after state, the two collide, they're going to stick together, as arrows in wood tend to do. And what would you kind of expect the log to do at this point? Say it again, sorry. It'll move. Do you expect it to move a lot? No. It might just barely recoil, maybe enough to tip over, but it's definitely, like, you wouldn't expect it to rocket away at this speed, would you? No. And that's what we're going to prove. We're going to prove how barely the log recoils from this. Prove that that assumption is correct. Main thing I'll point out about this after state is that the arrow is going to stick into the log. So whatever that final speed is, they're going to share it. They're stuck together now, like the two boxes tied together over the pulley from a few weeks ago. So we don't know what the final speed is, but it's just one VF, conveniently. And in this scenario, whatever momentum the arrow brought is now going to be shared across both objects, because the arrow is going to slow down. It's going to give up a lot of its momentum to do so, and the log will technically speed up, not by a lot, but it will. And in order for it to begin moving, it needs momentum. It's going to take momentum from the arrow so that it can get itself moving. So, any issues with the initial premise before we start applying math to it? All right. We're going to be examining the conservation of momentum in this scenario. So I'm going to treat this as the starting point for our collision question. Total momentum initial equals total momentum final. That means we need to add up the two initial momentums of the two objects. Actually, the plural of momentum is momenta. So we're going to add up the two momenta of the objects. It's kind of the same way the plural of curriculum is curricula. Is that Latin? I don't know. Whatever language it is, we need to find the initial momenta of the two objects and add them together, and then compare that to the sum of the final momenta of each separate object. So on the before side, I have listed momentum arrow initial and momentum log initial added together to create the total, because those are the only two objects here. They're the only two things that could have momentum. And on the final side, we've got the same two objects, but looking at their final momenta instead. So the two sides will pretty heavily mirror one another. Where'd my good marker go? There we are. Now on the initial side, I've already asked you this, where does all the momentum live over here? Arrow. Formula for momentum is mass times velocity. So to further elaborate, we've got mass arrow times velocity arrow initial plus mass log times velocity log initial. And we know velocity log initial is 0. So this whole term is eventually just going to go away. Arrow is bringing all the momentum. Log doesn't bring any. Instead, it insists that the arrows share. Final side will look pretty similarly, because it's the same two objects with the same two masses. An object's mass doesn't usually change unless you physically break it, and then you just have multiple smaller objects. So the momentum final for the arrow will be the arrow's mass times its final velocity, and likewise the logs will be its mass times final velocity. Conveniently, as earlier stated, they will have the same final velocity. So rather than two different final velocities, it's just one, the same variable listed twice. This is the most convenient way this problem could work out. If the objects instead bounced off of each other at different speeds, we'd have two different VFs to find, and that requires more math. So we're starting with this case. It is always more convenient numerically when the objects stick together and share a final speed. Any questions on this initial setup before we start putting numbers in? I'm writing everything out so you can kind of see the more general term before you say, look at the homework. All right. We know everything here except VF, so we can start plugging in our numbers. We got mass arrow. Am I going to write 10? What am I going to write? 0.01 times the arrow's initial speed of 25. Log, mass of 5 kilograms, but initial velocity of 0. So once again, this whole term's just going to go away. On the after side, the masses stay the same, but we will multiply them each separately by the one united final velocity. Once again, trying to demonstrate that the arrow brings all the momentum, and then in the final state, that momentum is going to be shared unevenly between both the log and the arrow that's now stuck in it. The left side is going to boil down entirely to just 0.25, so I'm just going to go ahead and cut out the 5 times 0 term, 0.25. And on the right, VF's the only unknown, so I'm just going to use the distributive property. VF, open parentheses, 0.01 plus 5, close parentheses. And so, second to last step, VF should equal 0.25 over 5.01. So everyone see how that works? Does anyone not see how that works? All right. Now, I believe this should give us something to the tune of 0.049 repeating infinitely forever, or something to that effect. It's basically 0.05, and if we rounded it, it would be. I'm just going to keep the 9 repeating to emphasize a point later. You know what, I'll make it 2 9s repeating. That line above the numbers just means the repeating forever thing on your calculator. Oh, and that's a velocity, so units to meters per second.
It actually isn't repeating forever.
It isn't.
499001996.
All right. Thank you very much. I'll just take off the repeating forever part. Thank you. And that is the shared final velocity of the two objects. And as we guessed earlier, the log does not move very fast as a result of this. You might not even notice the recoil. Probably definitely, I'm fairly certain it wouldn't even fall off the fence post. That's what I'm trying to say.
Then we have to implement that into the equation to find the final?
Well, this is the final velocity.
Oh, final momentum.
Is that what I asked? How fast? Yeah.
How much
Oh.
momentum is in the system after the collision ends?
I got ahead of myself. You're right. Well, we kind of already know that answer because we figured out how much momentum is initially in the system.
Yeah.
And technically, this would also be the momentum afterwards too, but I will prove that. Thank you for asking. Let's take this number, put it here, and prove that it works. So 0.25 equals 0.0499 times 5.01. Does that equal correctly? Barring any minor rounding thing. So this should give you 0.25 equals 0.25, thus proving the momentum is conserved. Furthermore, I can also individually calculate each object's specific final momentum. Momentum arrow final would be 0.01 times 0.0499, therefore 0.00499. And final momentum log would be 5 times 0.0499, and that should be wait, I missed the 0 actually. something like this. So that would be the specific final momentum of each object if treated separately. Note how they add up to 0.25. This also shows, again, the arrow lost pretty much all of its momentum. It had to give most of it up to even get the log to budge. So even though the final velocity is shared, each single object does not have like half of the total momentum. The momentum is unevenly shared to guarantee the same final speed if they stick together. Does that make sense? All right, how's this one feel? Does it match up with your expectations and experience of reality? All right. The next week will look very similar to this. We're going to look at different types of collisions to see how the momentum is conserved and transferred between objects within those collisions. And at a certain point, we're also going to rope kinetic energy back into it, kind of see how it works in different types of collisions as well. That will also notably be what lab next week is about. You will be causing collisions and measuring momentum and kinetic energy before and after. Namely, the collisions will be on those air tracks that we used 2 weeks ago at this point. It rams two things together in a frictionless environment to see the speeds at which they move after the fact. Now, before you can start packing up, we've got through all the official stuff. I just want to make one more quick point before we break for the day. Momentum is always conserved, even when it doesn't look like it is. I'm going to refer back to this scenario again, where I dropped the golf ball on the table, noise incoming. The fact that the golf ball didn't come back to the same height indicates that it actually did also lose momentum on impact in addition to energy. Because if it had the same momentum before and after, it should still rise to the same height. So momentum is a little less pesky than kinetic energy because it only has the one form it can take, but you can still lose it. It's still conserved, it still exists, it's just not in the golf ball anymore. But it is conserved, it's just in the desk now. Now, to give another example, I'm now going to throw this at the wall, so further noise ahead. Wow, multiple noises. Same thing technically just happened. The ball ricochets off of the wall. Technically, the ball would impart some of its momentum into the wall. If the wall has momentum, it should also have a velocity, right? So if momentum is conserved, why does the wall not shoot off that way? If momentum's conserved, if some momentum left the golf ball and entered the wall, why was the wall not moving?
It exerted a greater force onto the ball than the ball exerted on it.
Technically, they would exert the same force on each other because of Newton's third law. Whenever one acts on the other acts back, equal and opposite. It's actually, well, you're halfway there. It's the same force, but acting on very different masses. The golf ball's mass is tiny, so the force from the wall is going to accelerate it a lot and cause it to change direction. But what's the mass of a brick wall, especially one that's underground, backed up by dirt and rocks? Big, very big, too big. So that golf ball did not have that much momentum in it. I can't throw it that hard, and its mass is tiny. So the wall didn't gain much momentum, and that tiny amount of momentum is now shared across a massive brick wall. Frankly, it's shared across the entire building, since the building is pretty well attached. And again, that building is further backed up by the earth, since we are underground right now. So the teeny amount of momentum the wall gained is now dispersed across an incredibly large mass, meaning it did actually move, just incredibly slowly. Yes?
So if we throw the ball enough times, we can move this across the entire campus.
Yes.
Awesome.
But it would take numerous attempts. ideally you'd be chucking a much larger projectile, and you probably have to throw it in Mach 2 to make much of a difference. Frankly, you'd sooner just blow a hole in the wall than move the building. Like, if you fired a cannon at the wall, you'd sooner make a crater and dig through the dirt than you'd actually knock the building over. But it's hypothetically possible if you can distribute the force evenly across the whole building. But yeah, you're right. If you right scenario, you can make something like that happen. But this is ultimately why sometimes the momentum doesn't look like it's conserved if you say, run one object into a very big, very sturdy object. But it technically is. And this is also why when you drop things on the ground, sometimes it looks like the momentum just vanishes, right? Like old Looney Tunes cartoons, anvil falls off cliff, anvil hits ground, anvil comes to a dead stop. Where'd the momentum go? It went into the earth. And the earth, the mass of the earth is 24 zeros. So the earth's not moving because of that. Teeny tiny velocity. And frankly, every single second, objects all over the earth are dropping onto the surface in every direction. So any tiny little bit of velocity it gains from you dropping something, someone in Australia is canceling that out by dropping something else. So the momentum's conserved even when it doesn't look like it is. And thankfully, because the earth is so massive, that prevents the earth from being knocked around by things hitting it, which is good because this keeps every single meteor from knocking us off our axis. It takes a very big meteor to do that. I mean, frankly, we'd have bigger problems before the axis tilted if a meteor that big was approaching. Questions? All right, let me know if you need anything, including but not limited to questions about your midterm or your test. And have a great day. We're back to normal lab schedule next week. Yeah. Remind me your last name?
Why?
Your current score